In this video, I'll show you how to convert denary numbers into normalised floating point binary. This means I'll also be discussing the importance of normalisation and, of course, how to do it. Let's quickly recap how to convert from binary to denary. Suppose you want to convert this binary number into base 10 and that you have a 4-bit mantissa and a 4-bit exponent, both in 2's complement. The first thing I'm going to do is rewrite it. I'm just separating the mantissa from the exponent and establishing where the binary point currently is, immediately after the sign bit. I can see this is a positive number. Then I work out the value of the exponent. In this case, it's 2 to the power of 3. By the way, when I say times 2 to the power of 3, it means float the point 3 places to the right. But it might have occurred to you that 2 to the power of 3 is 8, which of course it is. If you move the decimal point of a base 10 number 1 place to the right, you're multiplying it by 10. Move it 3 places and you're multiplying by 10 3 times, that is, by 1,000. In binary, when you float the point 1 place to the right, you are in fact doubling the value. Floating it 3 places to the right means you're doubling it 3 times. In other words, you're multiplying by 8. Anyway, I now have my number in pure binary, which I can convert into denary. So, my original binary number is 7 in base 10. Let's do that again with a 4-bit mantissa and a 4-bit exponent. I can see that the exponent this time is a negative number, which means I'm going to float the point to the left 2 places. Convert the pure binary number into denary, and this time I have 0.21875 in base 10. To convert from denary to floating point binary, you essentially need to perform the same process in reverse. Let's start with positive denary numbers. For example, 7. We have 4 bits for the mantissa and 4 bits for the exponent, both in 2's complement. First, calculate 7 in pure binary. Now, and this is the crucial step, reposition the binary point such that it occurs immediately to the left of the leftmost 1. Bear in mind that because you're representing a positive denary number, the first bit, that is, the sign bit, must be a 0. This means that for a positive number, the mantissa should start with a 0 followed by a 1. I'll say more about that in a few minutes. For now, just follow the recipe. In order to get this binary point back to its original position, you would need to float it 3 places to the right. This gives you an exponent of positive 3. Calculate the exponent in binary and represent it using the number of bits that have been allocated for the exponent. In this case, the number 3 is represented with 4 bits as 0011. And this will give you the floating point binary representation of 7 that you're looking for. Let's see another example. This time we want to represent 1.5. Again, we're using 4 bits for the mantissa and 4 bits for the exponent, both in 2's complement. First, calculate 1.5 in pure binary. Now for the crucial step. Reposition the binary point so that it occurs immediately to the left of the leftmost 1. 1.5 is a positive number, so the sign bit must be a 0. And, just like in the last example, this must be followed immediately by a 1. Because you're using a 4-bit mantissa, you need to pad it out with an extra 0 on the right-hand side. In order to get this binary point back into its original position, you would have to float it 1 place to the right. This gives you the value of the exponent, positive 1. Calculate the exponent in binary and represent it using the number of bits that have been allocated to the exponent. In this case, the number 1, represented with 4 bits, is 0001. So here is the floating point binary representation of 1.5 that we're looking for. Let's see one more positive number for now. This time 0.25. Again, we're using 4 bits for the mantissa and 4 bits for the exponent, both in 2's complement. First, calculate 0.25 in pure binary. Reposition the binary point so it sits immediately to the left of the leftmost 1. This time we're moving it to the right to ensure that we have a sign bit of 0 followed by a 1. This makes the original leftmost 0 redundant. We also need to pad out the mantissa on the right hand side with a couple of extra zeros to make it up to 4 bits. In order to get this binary point back into its original position, you'd have to float it 1 place to the left. This gives you an exponent of -1. -1 in 4-bit binary is 4 ones. So here is 0.25 in floating point binary. Before continuing, you should make sure that you understand the methods that you've seen so far. The best way to do that is to try some conversions for yourself. Pause the video now if you want to give these conversions a try, and I'll show you the solutions in a moment. And here are the solutions. Notice how they all start with a 0 followed by a 1. Here's a couple more for you to try. This time you're being asked to represent these denary values using 10 bits for the mantissa and 6 bits for the exponent. The method is exactly the same. And here are the solutions. Notice again that they both start with a 0 followed immediately by a 1. Now let's consider some examples of negative denary number conversions. For example, -6. First, calculate -6 in pure binary. For a negative number, the leftmost 1 has a negative place value. Now, reposition the binary point so that it's immediately to the left of the leftmost 0. Bear in mind that because we're representing a negative denary number, the first bit, the sign bit, must be a 1. This means that for a negative number, the mantissa should start with a 1 followed by a 0. In order to get this binary point back into its original position, you'd have to float it 3 places to the right. This gives you the value of the exponent, +3. And we express this exponent in binary, and we have the result, -6. Now let's try -1.5. First, calculate -1.5 in pure binary. For a negative number in pure binary, the leftmost 1 has a negative place value. So here, -2 plus 0.5 is -1.5. Before I continue, note that you could represent -1.5 in pure binary like this, because -4 plus 2 is -2. Or you could do it like this, because -8 plus 4 plus 2 is also -2. In fact, you could have a string of 1s on the left hand side of this and it would still be -1.5, as long as the leftmost 1 had a negative place value. For a negative number, leading 1s are as useless as leading 0s in a positive number. Ultimately, you want to arrive at a representation of a negative number that will use the mantissa as efficiently as possible. This means using as few 1s as possible. Now, reposition the binary point so that it occurs immediately to the left of the leftmost 0. Bear in mind that because we're representing a negative denary number, the sign bit must be a 1. This means that for a negative number, the mantissa should start with a 1 followed by a 0. Pad out the mantissa on the right hand side with zeros to make sure it contains 4 bits. In order to get this binary point back into its original position, you'd have to float it 1 place to the right, so this gives you an exponent of +1. Convert the exponent into binary and we have our result. Once again, you should make sure that you understand the methods you've seen so far before continuing. Here are some conversions you can try yourself. Pause the video now if you want to give them a go, and I'll show you the solutions in a moment. And here are the solutions. Remember, for a negative number, the leftmost one has a negative place value. Notice how all of these solutions start with a 1 followed by a 0. And here's a couple more for you to try. This time we're using 10 bits for the mantissa and 6 bits for the exponent. And here are the solutions. Notice again they both start with a 1 followed by a 0. This is what you would expect of a normalised negative number. Let's talk about normalisation. This was our floating point binary representation of 0.25 with a 4-bit mantissa and a 4-bit exponent. Let's convert it back into denary just to make sure it's correct. And indeed it is. Now let's convert this binary number back into base 10 using exactly the same method. This is also 0.25. Here's another example, a different binary number. We'll convert it into denary using the same method. This time we're not floating the point at all because we have an exponent of 2 to the power of 0. And once again we have 0.25. We have 3 different floating point binary representations of 0.25 using 4 bits for the mantissa and 4 for the exponent. So which one is correct? Well, they all are, but only one of these values is normalised. Let's consider standard scientific form again. This is the speed of light in a vacuum, expressed in meters per second. To convert this into a regular number, we float the decimal point 8 places to the right. But this is also the speed of light. The decimal point is starting in a different position, so it only needs to float 7 places to the right. And this is the speed of light too. And so is this, and so is this. So which is correct? Well, strictly speaking, they all are. The top 3 of these representations yield the same value when we float the point according to the exponent, but notice how the last 2 are not as accurate as the others. This is the normalised form. By putting the decimal point immediately to the right of the most significant digit in a fixed sized mantissa, we strike the best balance between range and precision. The same applies in binary. For a given sized mantissa and a given sized exponent, there are usually several perfectly accurate representations of the same value, but only one of them is normalised. In the case of 0.25 in this 4x4 register, the first representation shown here is the normalised form, the one in which the sign bit of 0 is followed immediately by a 1. The objectives of normalising floating point binary numbers include to maximise the precision of a floating point binary number, and, generally speaking, this allows us to achieve the most accurate representation for a given sized mantissa. Normalisation also means we have an unambiguous representation of a value. I'll show you in a later video that arithmetic operations involving floating point numbers are greatly simplified if the numbers are normalised, because algorithms know that the numbers will always be in this form. If you've converted from denary to floating point binary, in the way I've already described, you'll end up with a normalised representation and there's nothing more to do. You can easily spot a normalised floating point binary number because, for positive numbers, the normalised form starts with a 0 followed immediately by a 1. For negative numbers, the normalised form starts with a 1 followed immediately by a 0. If you're dealing with something that isn't already normalised, then normalising it is a fairly simple business. If you wish, you could take the long way around by converting it back into denary and then back into binary again, using the methods I've shown you. But essentially, all you need to do is get the binary point in the correct position and then adjust the exponent accordingly. Here's an example. You can see straight away that this isn't normalised because it starts with 3 zeros. First, decide if you're dealing with a positive or a negative number. Clearly this is positive because the leftmost bit, the sign bit, is a 0. And remember, the binary point is positioned immediately to the right of the sign bit. Notice the current value of the exponent. In this case, it's 1. Reposition the point so it sits immediately to the left of the leftmost 1. A positive number must start with 0, 1. Now, get rid of any meaningless zeros on the left-hand side and pad out the right-hand side of the mantissa with zeros so you have 4 bits altogether. Calculate a new value for the exponent. In this case, the point was moved 2 places to the right, so you need to subtract 2 from the current exponent. This gives a new exponent of -1. And don't forget to express the new exponent in binary. Until you're confident with this method, it's probably wise to convert the normalised form and the un-normalised form back into denary to make sure that they are indeed alternative representations of the same number. You've seen this particular value before. It's 0.25. Let's do another one. You can see this is not normalised because it starts with 2 zeros. First, decide if you're dealing with a positive or a negative number. This must be positive because the sign bit is 0. The binary point is located to the right of the sign bit. Notice the current value of the exponent, in this case -1. Reposition the point to the immediate left of the leftmost 1. You want the mantissa to start with 0, 1. Get rid of any meaningless zeros on the left-hand side and pad out the right-hand side of the mantissa so you have 4 bits. Calculate a new value for the exponent. In this case, the point was moved 1 place to the right, so you need to subtract 1 from the current exponent. This gives a new exponent of -2. Express this in binary, and to check it's correct, you could convert both forms into denary. They should be the same. This time, let's normalise a negative number. The sign bit is 1, which means it's negative, but you can see it isn't normalised because it starts with 2 1s. At the moment, the binary point is immediately after the sign bit. Notice the current value of the exponent. Reposition the point so it sits immediately to the left of the leftmost 0. A negative number must start with 1, 0. Leading 1s are superfluous, so get rid of them and pad out the right-hand side of the mantissa with zeros so you've got 4 bits. Calculate a new value for the exponent. In this case, the point was moved 1 place to the right, so you need to subtract 1 from the current exponent. This gives a new exponent of 0. Express the new exponent in binary, and you may recognise this result as -1. Convert both forms back into denary if you want to be sure. Let's do one more negative number to be sure of the process. For a change, we have a 5-bit mantissa and a 3-bit exponent. The sign bit is 1, which means that this is negative, but it isn't normalised because it starts with 3 1s. Note the current position of the binary point and the current value of the exponent, in this case 3. Move the point to the left of the leftmost 0. Remove any leading 1s, so the mantissa starts with 1 0, and pad it out to a total of 5 bits. The point was moved 2 places to the right, so subtracting 2 from 3 will give us a new exponent of 1. This is the normalised form. If you convert both forms back into denary, you'll see they both represent minus 1.5. Here's a couple of floating point binary numbers that you can normalise yourself to check your understanding. Notice they're stored with a 5-bit mantissa and a 3-bit exponent. Pause the video if you want to give them a try, and I'll show you the solutions in a moment. And here are the solutions, with the denary values for cross-checking. And a couple more examples, this time with a 10-bit mantissa and a 6-bit exponent. Solutions in a moment. And here are the solutions. Again, with the denary values, so you can cross-check them. Now, by the way, I just want to be clear. When you calculate a new value for the exponent, you always subtract something from it. Because if it's a positive number, we're trying to get rid of leading zeros. If it's a negative number, we're trying to get rid of leading ones. This means that we need to make the exponent smaller than it already was. In summary, normalisation maximises precision for a given sized mantissa. When converting from denary to floating point binary, we should aim for the normalised form. Normalisation allows for an unambiguous representation of a floating point number. This is important because processor hardware usually expects numbers to be in a particular format. For positive numbers, the normalised form starts with 0, 1. For negative numbers, the normalised form starts with 1, 0.